Welcome to Year 8, Competence-Based Middle Years Program Level 3, Sciences. Session number 4. In this session, we are going to analyze uniformly accelerated circular motion, Y8C. Let's consider a body moving along a circumference in such a way that it covers increasing distances per unit of time. We will say that the body has an angular acceleration represented by the Greek letter alpha. Alpha, the average angular acceleration, will be the variation in the angular speed divided by the time it takes to have that variation. The units for the angular acceleration are radians per second squared. The dimensions of alpha will be the dimensions of radians divided by second squared. The dimension of radian is 1, therefore it will be 1 divided by time squared, which equals time 2 minus 2. Similarly to what happens in the uniformly accelerated rectilinear motion, in the uniformly accelerated circular motion, the angular speed omega equals the initial angular speed omega 0 plus alpha, the angular acceleration, times time. And also similarly to what happens in the uniformly accelerated rectilinear motion, phi, the angle swept, equals the initial angle plus the initial angular speed omega 0 times the time plus a half of the angular acceleration times the time squared. The tangent acceleration, meaning the linear acceleration tangent to the trajectory that the moving body has, equals the angular acceleration times the radius. Let's see a numerical example to make it clear. Car's wheels measure 0.6 meters in their diameters. It uniformly accelerates from being still, obviously, to 30 meters per second in 6 seconds. Find out for a point on the wheel's brim at that moment, at the end of the 6 seconds, A, the angular speed in radians per second and rotations per second, B, the angular acceleration, C, the normal acceleration, and D, the car's acceleration and the distance covered since it started moving. Let's answer the first 2 questions. This is our car, and let's focus on the wheel. Please forgive the PowerPoint effects that seem to make the wheel rotate the other way around. But just consider what happens when the wheel does an entire turn as the car rolls along the road. As the wheel rotates an entire turn, the distance covered equals 2 pi times the radius. Now we know that the speed equals the angular speed times the radius. Therefore, the angular speed equals the speed, linear speed, divided by the radius, the linear speed of the car divided by the radius of the wheel. We know that the linear speed of the car is 30 meters per second, and we know that the radius, half diameter, is 0.3 meters. Therefore, it is 100 radians per second. Now, a whole rotation is 2 pi radians. Therefore, that angular speed of 100 radians per second divided by 2 pi radians per rotation means 50 divided by pi rotations per second. By the time that linear speed and that angular speed of the wheel are reached, we can say that the angular speed of the wheel equals the initial angular speed when it started and it was in rest, plus the angular acceleration times the time. Therefore, 100 radians per second, which is the current angular speed, equals 0 because it started from rest, plus alpha times the 6 seconds that have elapsed. Therefore, the angular acceleration equals the 100 radians per second of the current angular speed divided by the 6 seconds it's taken to reach that angular speed, which is 50 divided by 3 radians per second squared. Now we will consider the last two questions. The normal acceleration of a point on the brim of the car's wheel plus the car's acceleration, linear acceleration, and the distance it's covered since the start of the movement. As we know, the normal acceleration equals the angular speed squared times the radius. We have already calculated the angular speed at that moment, and it is 50 divided by pi. Therefore, that squared in brackets times 0.3, which is the radius, and that equals 2500 divided by pi squared times 0.3. 2500 times 0.3 divided by pi squared, which is 750 divided by pi squared meters per second squared. We know that pi squared roughly equals 10, therefore that is approximately equal 75 meters per second squared. Let's now stop for a second here. We know that gravity equals 9.8 meters per second squared, and we have now the wheel of a car whose radius is 30 centimeters, 0.3 meters. It is rotating at a rate that allows the car to cover 30 meters per second, 108 kilometers per hour. We'll see that in another occasion. And the normal acceleration, meaning the acceleration towards the center of every single point on the brim of the car, is 75 meters per second squared, roughly 7.5 times the acceleration of gravity. That is the huge value of the normal acceleration that is needed to hold together the pieces of everything that is rotating. That is why when we hold hands and we turn in circles, we really need to hold strongly and not let the other person go to keep rotating. Rotation involves huge normal accelerations. Let's now move on to the car's linear acceleration. We know that in uniformly accelerated rectilinear motion, speed v equals initial speed v0 plus the acceleration times time. We were at rest at the beginning, therefore 30, the current linear speed, equals 0 plus the linear acceleration times the 6 seconds elapsed. Acceleration equals 30 meters per second we have now as linear speed divided by the 6 seconds it's taken us to reach it, which means 5 meters per second squared. The distance covered from the beginning of the movement will be r, final distance, equals r0, position at time 0, which in our case is the origin of coordinates, therefore 0, plus initial speed, which is 0, we started from rest, times the time, plus a half of the acceleration times the time squared. That is 0 plus 0 plus a half of the acceleration times the time squared, which equals 90 meters. That's the distance covered in those 6 seconds. And this is the end of this session. As always, in science and in life, enjoy.